Life. What does life want to do? Well, it wants to survive. But obviously, an organism can't live forever. And so the next best thing it can do is to make sure that the next generation, its children, its grandchildren, and so on and so forth, survives. And ultimately, its species survives. And to do that, they need to preserve their habitat so that the next generation has somewhere habitable to live. But right now, as humans, we're destroying our habitat, Earth. And so ultimately in the future, our species won't be able to survive. Now, it all started with the Industrial Revolution. The Industrial Revolution was a monumental step forward for our civilization, but it solidified our impact on this planet in the wrong way. Billions of tons of carbon dioxide have since been emitted into our atmosphere, millions of forests have been destroyed, and a staggering 2/3 of the world's wildlife populations have plummeted in the last 50 years. No matter how much we improve our technology to tackle this problem, climate change, it will continue to haunt us. The main issue lies in the system itself. The Industrial Revolution introduced the heat, beat, and treat system. This system heats materials at high temperatures, beats them with large amounts of pressure, and treats them with toxic chemicals. This system requires massive amounts of energy and produces lots of waste that is usually not recyclable. And this is seen no better than in our own cities. Over half of our population lives in urban areas, despite only making up 3% of the entire globe. This 3% accounts for over 75% of the entire carbon emissions. Changing these urban environments will be a major factor in overcoming climate change. We need a new revolution, one inspired by nature. But why nature, you may ask? Well, nature has been evolving and growing for 4.5 billion years, with life introduced around 3.7 billion years ago. If the age of the Earth was a calendar year and today was just before midnight on New Year's Eve, humans showed up nearly 15 minutes ago, with all of our recorded history only spanning 60 seconds. And so, believing that we are somehow better than nature is ridiculously naive. Despite our current path in driving away from nature, we are as much a part of it as a fly on your window. Believe it or not, we are still vulnerable to natural selection and other environmental factors. If we don't start trying to adapt to these ecosystems will adapt to us. The best way of doing that is to not extract from nature, but instead to learn from it. Our relationship with nature can be described with the 3 H's: harvest, harness, and harmony. The first H details our reliance on nature for providing us with food, water, and air to breathe. The second H represents our intelligent evolution and how we've been able to build civilizations by utilizing things like wood, stone, metal, and other resources. The last H is the most important. It embodies our understanding of nature. Instead of taking from it, we can learn from it. We can understand how nature was able to solve the problems that we're facing now and apply it to our own designs. We could bring about a new revolution, one in which we benefit the planet instead of harming it. This emulation of nature is known as biomimicry. The term originates from the Greek word bios, which means life, and the word mimikos, which means imitate. Janine Benyus coined this term in her book Biomimicry: Innovation Inspired by Nature. This book propelled this field of science forward in terms of popularity and exposure. But although the spark of interest was very recent, this field of science goes back thousands of years to our very first ancestors. As the first cavemen left their caves, they mimicked the sharp teeth and claws of the beasts they encountered to make spears and knives. Fast forward to Leonardo da Vinci, who studied the physicality and behavior of birds in hopes of making the world's first flying machine. Although he was unsuccessful, his research later allowed the Wright brothers to achieve flight for the first time. More recently, advances in gene editing have all been thanks to mimicking the defenses of bacteria. This new system, called CRISPR, uses the system in which bacteria can detect and basically eliminate viruses using enzymes like Cas9. But despite humans unconsciously or consciously practicing biomimicry for generations, we're still only scratching the surface of what is possible. There are 3 main types of biomimicry. Organism, which includes mimicking an organism's form, function, and even its materials. Second, behavior, which is mimicking an organism's behavior and interaction with its environment. And third, the ecosystem, mimicking the entire ecosystem with all the organisms and all the factors. Most of the cases of biomimicry seen today utilize the first two types of biomimicry. This is known as ad hoc, when one mimics a specific organism to achieve a specific function to solve a specific problem. To completely reimagine our urban centers, we need to mimic an entire ecosystem. However, this is a lot easier said than done, as ecosystems are a lot trickier to mimic, as they have a lot of factors to account for. In ad hoc biomimicry, we can focus on one singular function for one specific problem. However, for ecosystem biomimicry, we have a whole community of organisms and functions to handle. The idea of mimicking an entire system allows something known as regenerative design to be possible. The regenerative design aims to address the continued degradation of ecosystems in our biosphere by designing and developing built urban cities to restore and heal the ecosystems for the mutual benefit of both nature and humanity. Because regenerative design mimics the environment and the ecosystem, it must also adhere to the ecosystem principles that are laid in place. These ecosystem principles are as follows. Nature uses sunlight as its main energy source. There are exceptions, but generally, nature uses only the energy it needs. Nature fits form to function. Nature recycles everything. Nature rewards cooperation. It focuses on the entire system rather than the individual components. Nature thrives with biodiversity. Nature demands local expertise and is reliant on local conditions. Nature curbs excesses from within. Basically, excesses like the overuse of energy, food, or water is controlled. And thus, nature knows the power of limits. It takes its limits seriously. With the basic idea of what ecosystem principles are, how do we start catering them to regenerative design in urban environments? Well, we can start by understanding why an ecosystem is better than our urban cities. Humans use a linear system of energy in built environments. Thus, we are left with a lot of waste. In contrast, ecosystems use a closed-loop system. This doesn't have any waste, instead filtering it back into the system, completing the cycle. For example, a typical product in a store goes through these steps. First, the raw resources are harvested by extracting them from the ecosystem, and this has very negative consequences like habitat and biodiversity loss. Second, the raw materials are then transported to a factory where they're processed through the heat, beat, and treat system. This step produces tons of waste, both in solid, liquid, and gas form. Third, the manufactured product is transported to be sold, getting shelved in stores, and then we consumers buy all these products to use in our lives. And finally, the product is thrown out after it serves its purpose, becoming a piece of waste that degrades our environment. In contrast, nature has a far better solution. It follows the ecosystem principles mentioned above to create a sustainable system. For instance, the sun provides energy to the plants in this environment, in turn allowing the plants to produce energy via photosynthesis. This energy is then consumed by primary consumers, secondary consumers, etc., until it reaches the top tertiary predator. Although this can be substituted for any other organism, when the top predator dies, its remains are decomposed by decomposers like beetles and earthworms. With the organic matter decomposed, it can be absorbed back into the soil, providing nutrients for the next plant to start the cycle again. By regulating their waste back into the cycle, they benefit the earth and its inhabitants, including us. These benefits are known as ecosystem services. They either directly or indirectly impact us humans. They can be divided into three main categories: provisioning services, regulation services, and supporting services. Many sources also credit a fourth service, which is cultural services. It can include artistic inspiration and ideas, and it's very similar to biomimicry. Within provisioning services, there's food, biochemicals, raw materials, fuel energy, fresh water, and genetic information. Regulating services include pollination, seed disposal, biological control, climate regulations, prevention of disturbance and moderation of extremes, decomposition, and purification. And finally, supporting services include soil, formation, retention, fertility or quality, fixation of solar energy, nutrient cycling, habitat provision, and species maintenance. Out of all of these services, 7 have been selected as the most suitable to be integrated into our urban designs, and they are as follows: food, fuel energy, fresh water, climate regulations, purification, nutrient cycling, and habitat provision. So after identifying the ecosystem services we want to focus on, we can start to analyze and identify how they correlate with our urban environment. In the place of every city in the world, there once stood an ecosystem. So, by comparing the data for what the ecosystem provided to what the environment lacks, to what the urban environment lacks, we can create a better plan moving forward on how to apply these ecosystem principles to the necessary designs. Now, this is known as Ecosystem Services Analysis, ESA, where we take a closer look at the correlation between ecosystem services and our urban environments. The first step in ESA is to determine if there is a healthy ecosystem in the locality that can be studied. If not, the ecosystem that existed before development on the site would also work. Measurable rates of ecosystem services can then be determined. For instance, measurings like annual rainfall or water retention in a particular place relate to the provision of fresh water. Although there are still considerable gaps with the ecological knowledge of ecosystem services, they still each have aspects that can be measured, and these measurements can help determine the optimal environmental performance of the built environment that is or will be on the same site of the ecosystem. The final stage of ESA would then be to make sure these new changes brought to improve ecological urban performance don't negatively impact other ecosystem services, and this can be done by looking at the entire picture rather than individual components. So after identifying what certain areas need more ecological support, we can now utilize biomimicry and actually emulating nature's designs to tackle the problem in 3 cohesive steps. The first step would be the design literature precedent review. We need to identify already existing designs, technologies, materials, and even strategies within our urban environments that are suitable to be implemented into regenerative design. Now, there are many case studies available already that are implementing biomimicry to improve innovation. Now, in terms of materials, spider silk is extremely durable. They have low density tensile strength exceeding 1000 MPa, an extensibility of approximately 0.27, which is way beyond the yield strength of steel. Spentex Engineering has taken this and artificially mimicked it into a highly durable textile. In the field of structure, the Eiffel Tower actually mimics the structure of bones, especially the femur bone, to give it the curvature and unique designs. Bones, most specifically the thigh bone, have a high load capacity. What's more, bones are connected by joints, and nature disconnects these joints under extensive impact or sudden movement without harm to the bone, thus decreasing the area of damage, basically. This creates huge implications for the future of buildings that could potentially dislocate parts or absorb the energy of an impact. Structural engineers also are utilizing the brilliance of bees and their honeycombs to create earthquake-resistant buildings. Bees connect and direct one another through a waggle dance, creating vibrations. Honeycomb is a small structure, and so these vibrations are likened to earthquakes. To avoid disaster, the walls of the honeycomb absorb these vibrations. So by sandwiching these honeycomb designs into part of our buildings, we can create more earthquake-resistant structures. In terms of cooling, South Korea's thematic pavilion uses self-shading technology by mimicking a South African flower. The flower contracts its petals and opens them when a bird lands on them. Following this function, the pavilion has 90-degree flaps that open and close depending on if the sun is shining on it or not. In terms of thermal regulation, which is a critical component to the cooling of a building, we've taken inspiration from termites and their hills. Termite hills are constructed in an almond-like shape, with one central chimney and multiple side chimneys known as flutes. The flutes respond quickly to changes in temperature throughout the day, while the central chimney remains relatively stable. When the flutes are warmed from the midday sun and the center is cool, air expands and rises in the flutes, contracts and sinks in the chimney, and vice versa. This results in a 2-time daily convection current within the mound that regulates the air. The East Gate Center in Zimbabwe uses a similar system. Outside air gets absorbed through vents, and depending on if the building is hotter or cooler, the outside air gets cooled or heated. This air is then circulated through the floors via fans and eventually make their way out through the roof, starting the cycle again. In terms of lighting, a glass company called Ornilix mimics spider webs and their ability to avoid natural collisions. Spiders weave UV reflective strands of silk into their webs to prevent birds from flying into them, and this has been incorporated to make bird-friendly glass. In terms of purification in natural wetlands, as water flows into a wetland, it encounters the plants there. and these plants slow the water down and absorb nitrogen and phosphorus nutrient pollutants. In addition, the slowing down of the water allows any sediment to flow down to the bottom. This system is recreated to suit our water purification needs in an artificial wetland. Finally, concretes can naturally absorb CO2 in the air in something known as the sponge effect. Similar to how a sponge absorbs water, the sponge effect is a result of gradual carbonization that takes place in the concrete over a long time. Currently, estimates show that concrete absorbs roughly around 30% of the amount of carbon that cement production emits. However, researchers found that adding small portions of nanoscale titanium dioxide to the cement can actually double this amount. Just like trees, this type of concrete allows buildings to absorb CO2 into their outer shell. The second step would be the relational database. The results of the first step would now have to be compiled into one collection of data, identifying connections, relationships between designs, technology, and ecosystem services. And then finally, the third system would take this database and make it into a model for easier visualization. All these steps and processes have actually already been used to produce the strategies for designing Urban Ecosystem Services Map version 1.0. This map utilizes an online mapping tool called Kumu to build a complex model of ecosystem biomimicry. There are a total of 341 elements on the map, equating to around 1,431 relationships. The outermost circle contains the case studies. The next circle in has the design strategies. The third circle categorizes ecosystem services categories. The second smallest circle contains the ecosystem services categories, and the innermost circle contains the ecosystem services types. The element colors were determined by the 7 ecosystem services most suitable for regenerative design. The size of each circle is determined by how many connections it has to other circles. By looking at the size of the circles, we can determine which of the 3 main ecosystem services have the most extensive knowledge and resources, and the ones that are lacking. Analyzing the map based on the number of connections to each element shows that provisioning services have the highest amount of connections, particularly the provision of fuel energy with a connection to 23 different design strategies, and the provision of fresh water with a connection to 15 design strategies. The map also showed that supporting services like nutrient cycling and soil building had the least amount of connections. The one exception to this was habitat provisions, as things like green roofs, living walls, gardens, etc. all are providing habitats for organisms already. The ecosystem subcategories with the least amount of knowledge associated with them were the provision of genetic information, fixation of solar energy, and the control of invasive species. Now this can be explained because all these all require the intervention of living plants. And so unless plant communities are integrated into urban design, these are actually kind of hard to achieve at the moment. Amongst all the technologies, strategies, and designs, revegetation has the most number of connections, suggesting that including more green spaces in cities will lead to more beneficial outcomes for other ecosystem services, like soil building. We have to be careful, however, not to allow these strategies and designs to just become simple technological add-ons. Rather, we need to fully understand the relationship underneath the surface to achieve regenerative design and the whole system. Now, the basis of this map was to illustrate the designs, strategies, and even technologies required to emulate natural ecosystems into regenerative urban environments already exist, suggesting that this isn't a technological or scientific obstacle, but rather a mindset one. We need to change our entire perspective on urban design, and people aren't really friendly to this big of a change. Now, ever since the release of Janine Benyus' book, Biomimicry, Innovation Inspired by Nature, this field of science has slowly been rising to the level of recognition it deserves. Organizations like Biomimicry 3.8 and the Biomimicry Institute have been created to give the public further exposure to the field of science. What's more, there's actually been a site called Ask Nature that has arisen. And this site allows a user to search up a problem and actually see how nature solves it, which I think is really cool. Some cities in the world are actually adapting some of these regenerative principles that I've mentioned. The city of Kalundborg, Denmark, has an industrial model where any unwanted resource becomes the wanted resource of another industry. In the nature-inspired city of Lavasa, India, The water management of a forest has been mimicked to allow for better water retention, preparing the city for the dry seasons. There are huge implications for this field of science in the future. Our cities and our planets will continue to be affected by the inevitable destruction of climate change. While it may be easier to deal with these issues in the short term by producing laws to reduce emissions or focusing on one aspect of the problem, it is crucial, it is vital to address the issue in the entire ecological context it stands in. We need change, and ecosystem biomimicry is where we will find that change, so that we can make sure our species lives on for generations to come.